So we're going to do a couple more examples of groups under addition this time. So our first one is going to be something called M sub 2R. So M2R. This is the set of all 2 by 2 matrices. So it's an array of 4 numbers, 2 rows, 2 columns, where A, B, C, and D are real numbers. So the 2 refers to the dimensions, it's 2 by 2, and the R there means the entries are all real numbers. So we have this 2 by 2 matrix with real numbers, the set of all of those. All right, this is a group under addition. And let's go through those properties and check and just see that they all work. So part 0 is, was it closed under addition? And so we want to check if I had 2 matrices, A, B, C, D, and E, F, G, H, and all of those A through H are all real numbers. If I add those, do I still get a 2 by 2 matrix made of real numbers? So the way we add matrices is just the corresponding terms, we add them. So the top left entry is A, and the top left entry of the second one is E. So the top left entry of the sum becomes A plus E. So we just sort of add up these corresponding entries. And the matrix we get looks like that. And so if A through H, all of those are real numbers, then certainly A plus E is a real number, B plus F is a real number, C plus G is a real number, and D plus H is a real number. And so the sum is in M2R, and so it is closed under addition. Okay, the associative property. So to do this associative property, we want to add 3 matrices, and we want to add it in 2 different orders. So we want to take A, B, C, D plus E, F, G, H first, and then add I, J, K, L to it. And we want to work through what does that equal. And so that means we're going to do it in sort of 2 steps. We're going to first add those 2 in the square brackets. So we get this thing we had above, A plus E, B plus F, C plus G, D plus H. And we're adding to that this I, J, K, L. And so total, we get this big sum, A plus E plus I, B plus F plus J. And that's our sum of the 3 matrices in that order. And then we want to compare that to, so what we're looking at, is this the same, whoops, is this the same as if I did, let me fix that, A, B, C, D plus the sum of E, F, G, H, and I, J, K, L, where this time I do that sum of the second 2 matrices first. And so here I'm going to skip a line here, and you should see if you can do it, but we're going to take that A, B, C, D, leave it just as is, add the 2, and then do the third addition, and what we're going to get in the end is A and E and I, B and F and J, C, G, K, and D, H, L, just like before. So what we're using here, what I didn't write down up here, is we're doing an associative property of just addition in the real numbers as part of this problem. So that A plus E plus I wrote it as a sum of 3 things. Really what we mean is that sum, right? We have A plus E first, and we're adding I to it. And so up here, we could think about all these parentheses like that. Down here, we're going to have something different. We're going to have the parentheses like this because we added those second matrices first. But because addition is associative in real numbers, this means this works. Okay, so it's associative. The set of 2 by 2 matrices is associative under addition. All right, property 2. There's an additive identity. And so what I need to do here is figure out what I can add, what 2 by 2 matrix I can add to just ABCD, a general one, to get ABCD back. And what we need to add here is 0, right? But in this set, the 0 matrix is what we mean. So we're adding the 0 matrix. That's the identity. So 0, 0, 0, 0 is an element of M2R, and it's the additive identity. So in this case, 0 isn't just the 0, the number. 0 is 0, the matrix, because we're talking about matrices. All right, part 3, the additive inverse of A, B, C, D. So I need to add something to that so that I get that additive identity 0, 0, 0, 0 back. And so you might know what this should be. It's just going to be the negatives of everything. And so this guy is the additive inverse of ABCD. Okay, and it's definitely still a 2 by 2 matrix. So minus A minus B minus C minus D is a 2 by 2 matrix with real number coefficients, and so we have additive inverses. So we have our 4 properties of a group closed under addition. Associative property worked. We had an additive identity, and we had additive inverses. Okay, so there's another group under addition. All right, another one, one that we're going to see a lot throughout this class. So this is going to be R and then square brackets X. This is the set of all polynomials with real number coefficients. So I'm going to write a generic one as A0 plus A1x plus A2x squared, dot, dot, dot. And then at some point it ends, so we'll call that an x to the n. And the condition on the a's is that all the ai's are in R for all I 0 through n. Okay, so this is the set of all polynomials with real coefficients. All right, so this is a group under addition. I know how to add 2 polynomials, and so this time I think maybe I'll do that addition and the associative, the closed under addition and the associative property just as sort of examples instead of trying to prove them in general. So an example of it being closed under addition is, if I take 2 polynomials, so 1 plus 3x plus x cubed, how about? And I add any other polynomial, so 2x minus x squared. What I get back is a polynomial. I get 1, looks like I get 5x, I get a minus x squared and a plus x cubed, and that's still a polynomial with real coefficients. Okay. Let's see, I need a new page. All right, so that's our example of closed. If we want to do an example of associative, we're going to again rely on the associative property of real numbers. So here, let's do some simple polynomials. What if I do 1 plus 3x plus 2 minus 4x as my first pair, and then I'm going to add polynomial 7 minus x to it. If I do this, so I get 1 plus 2 is 3, 3x minus 4x gives me a minus x. That's what's in the square brackets, and then I'm going to add 7 minus x to it. And I get, looks like 10 minus 2x. Okay. On the other hand, if I add it the other way, so 1 plus 3x plus square brackets, 2 minus 4x plus 7 minus x. If I do this out, I'm going to get the same thing. And the reason this is going to work is, again, because it doesn't matter if I add 1 and 2 and 7. It doesn't matter which order I add those in. Which pair I add first is what I mean. Okay, so let me finish this up. So it looks like we get 10, and a 3x minus 5x gives us minus 2x, just like before. And so we definitely are associative. And if you think this through, it'll work for whatever polynomials you have. All right, so the interesting parts here are those next couple of questions. So what's the additive identity? So this is part 2. What is our additive identity? So I want to be able to add something to a polynomial. If p of x is a polynomial, I want to add something to it so that it doesn't change the polynomial. And I think you know what that is. It's 0, right? But one thing that's a little weird about this is the 0 that's here. This is the 0 polynomial. And so you might want to think about it as like not just the number 0, but maybe we can write it as 0 of x. It's a polynomial, but it's a polynomial with all 0 coefficients. Okay, so the 0 polynomial is our additive identity. All right, and then part 3, inverses. So if I had, let's do another example for this. If I do an example of inverses, if I had the polynomial 2 minus x squared plus x to the 4th, and I need to know what to add to it to get that 0 polynomial, what I need to add is minus 2 plus x squared minus x to the 4th. Okay, and so this guy, still polynomial with real coefficients. And one thing to note here is remember that this is the 0 polynomial, not 0 the number, but the 0 polynomial. Okay, so set of polynomials with real number coefficients is also a group under addition.